let us see how we can find out the values of zeta and omega n from the pole zero plot or S-plane. We have this generic form of a second order control system, which is h of s is equals to omega n square divided by s square plus 2 zeta omega n of s plus omega n square. So, first of all, we need to find out the poles of this transfer function, and for that we'll apply quadratic formula to this denominator term. This is also your characteristic equation. After applying the quadratic formula, we come up with two poles of this transfer function which are given here. The poles are minus omega n of zeta plus or minus omega n under root zeta square minus 1. So we have two poles here, one with the positive sign and the one with the negative sign. Okay, let us do some simple transformations. Let us take out minus 1 common from this denominator term, which is given here. So after taking out minus 1 common from this equation, it can be written as minus 1 bracket 1 minus zeta square, or we can also write it as minus omega n zeta plus or minus j omega n under root 1 minus zeta square. So we have converted this equation into a complex number. Assume sigma d is equals to minus omega n into zeta. Now we are naming it as damping factor. Let us assume that this imaginary term is equals to omega d, which is our damping frequency. So after using these two assumptions, we can write this equation as poles is equals to minus sigma d plus minus j omega d. So in the next step, we'll plot these two poles on the S-plane. How do we do that? First of all, let us assume that this is our x-axis, which we are representing by a term sigma, and this is our imaginary axis, which we are naming as j of omega. Now sigma d here is any real number, negative real number, and then we have omega d, which is an imaginary number. One is positive and the other one is negative. So in order to plot these two terms on this S-plane, assume sigma d is any negative number which is located here, and then omega d is any imaginary number which is located, the positive part is located here and the negative part is located here. Once we have marked sigma d and omega d on this S-plane, we can simply mark our pole. That is, one pole will be at the cross section of these two terms and the other one will be at the cross section of these two terms. In the next step, we'll find out how we can come up with the values of zeta and omega n from the S-plane. This is our pole zero plot of the generic form of a second order control system. Here we have two poles, one is located here and the other one is located here. The distance from the origin to this point is sigma of d, and the distance from the origin to this point and to this point is omega of d. We know that tan theta is equals to perpendicular upon base. So by using this S-plane graph, we know that this is our perpendicular and this is our base. So simply by putting these two terms into this equation, we can write it as omega d divided by sigma of d. But we already know that omega d is equals to this term and sigma d is equals to this term. So by putting the values of sigma d and omega d in this equation, we can write it as omega n under root 1 minus zeta square divided by omega n into zeta. Now we also know that tan of theta is equals to sine theta upon cos theta. So let us put this tan theta definition into this equation. So we can write equation 1 as sine of theta upon cos of theta is equals to omega n under root 1 minus zeta square divided by omega n of zeta. So we can cancel out these two terms, that is omega n will be cancelled out by this denominator omega n, and we will be left with only this equation, that is under root 1 minus zeta square divided by zeta. So if we compare the left hand side with this right hand side, we can write as sine of theta is equals to under root 1 minus zeta square, whereas cos of theta is equals to zeta. So using these two equations, we can easily find out what is our angle theta, or if we know theta, we can find out zeta by using either of these two equations. Now let us find out what is omega n. We have already discussed that the distance from the origin to the pole is omega n. But how we come up with this definition? We know that hypotenuse is equals to hypotenuse square is equals to base square plus perpendicular square. So we know that this is our base and this is our perpendicular. Simply by using these two terms into this equation, we can also write it as hypotenuse square is equals to sigma d square plus omega d square. But we also know that sigma d is equals to omega n of zeta, and omega d is equals to omega n under root 1 minus zeta square. So rather than using these two terms, we will be using their value. So after putting sigma d and omega d value into this base and perpendicular part, we can write it as hypotenuse square is equals to omega n square zeta square plus omega n square bracket 1 minus zeta square. So in the next step, we need to remove this square from the hypotenuse. For that, we are simply taking the under root of this right hand side, and we can also take out omega n square common from these two terms. After that, we will be left with zeta square plus 1 minus zeta square. We can cancel out these two terms because this is positive and this is negative, and we will be left with only this term, that is omega n square. So after taking out the under root of this term, we can say hypotenuse is equals to omega n, and this is our hypotenuse from the origin to this pole.